Welcome everyone. This is MLIR Open Design Meeting. I'm Alex. I'm also happen to be the presenter for Controllable Transformations in MLIR. This is a rehash of a talk I gave a couple of months ago at the MLIR Developer Summit with some more information and basically an attempt to record this thing that was not recorded before. Don't hesitate to interrupt me if you have questions. Raise a hand or speak. I'm not sure I will be able to see chat while presenting, but you can also try to chat. So Controllable Transformations talks about the transform dialect that I proposed almost a year ago, that has been in MLIR for multiple months and is now being more or less actively used in different projects for code generation. And in this presentation, I will first talk about why we decided to go for a transform dialect, how we do it, how one can use it, and then a more interesting discussion part is what are the effects it has on the MLIR infrastructure, and to some extent on how we think about building a compiler. So to answer the first question of why, well, we can look into several more or less successful compilers that use a sort of textual or separate schedule that separates the prescription of how something should be computed from what is being computed. So if you look at Halide and TVM and successor, if you look at FireIron, tensor comprehension, there are many more. All of them use some form of a schedule language or a schedule structure, or some passes in MLIR, namely in IRI, use a complex set of attributes to direct transformations to be performed by compiler. So we have a lot of evidence that at least there is a successful series of works that use separate schedules that are not part of the computation. And it's only reasonable to try and express these separate schedules in MLIR. So this dates back actually to the 90s, and there were a lot of work early on loop transformations for using some sort of schedules or trying to even define what transformations are. So to some extent, we can also say that declarative rewrite rules can be seen as schedules combined with the application or the rule of how they are applied to the IR. So there are several other things that we might gain by representing schedules separately, other than just being able to produce performance. One of the biggest things is this representation is declarative. So we can read it, we can analyze it with tools, we can supply it separately, so we can have the compiler understand what needs to be done for transformation that is separate, not hard-coded in C++, and more importantly, does not require to modify the compiler if you want to change the heuristic in the compiler. It also makes it cleaner for whoever looks at the computational code, because you separate the concern of what you're computing, say a convolution, from how you're computing it. Say you map it to a GPU and you move one of the things into a shared memory, another into registers, and so on. You don't really want to have that in your code that actually does the compute. Another thing about this being declarative is that it's processable by a compiler. So we can, for example, simplify the schedule. We can combine multiple schedules. We can, I don't know, have a tool learn how to produce a good schedule based on the input IR of what we're computing, or we can move the schedule and we can either execute it at compile time. So the compiler will look at your program and decide how it should be executed, or at runtime, at which point the compiler will generate the IR or the code that will decide which of the versions or how to further compile this at runtime. And several successful libraries actually do this to some extent. So libraries like 1DNN may choose based on runtime parameters of the computation which of the precompiled versions to use, and having the heuristic or the schedule as declarative thing actually lets us build this in an automated way. And one thing I will focus more in the third part of the talk is having this as a separate language lets us focus more on a particular part of the input IR we want to transform, rather than applying the transformations to the entire translation unit. So if you want to specifically optimize a very small part and spend a lot of time optimizing that part, and we can afford that, we can do just that. We don't need to optimize so deeply and waste compile time cycles optimizing things we know will have no effect on the final performance of the program. So now let's say there is enough good reasons to actually have this in the infrastructure. It doesn't mean everything should use it. Let's see how this can be done. And so far, I have been talking about schedules and DSLs and tools, but in MLIR, everything is a dialect. Like basically, when you come to MLIR and want to model something, you do a dialect. So logically, schedules in MLIR are also a dialect. We had to extend the dialect extension mechanism to allow clients to inject more ops. So basically, the worst case scenario could be that, well, each dialect or even pair or group of dialects or conversions come with a dialect for transforming that dialect. And it doubles or triples the number of dialects we have, and that quickly becomes less sustainable than the dialect system we already have. So instead, we only have one transform dialect, but we have an extension mechanism that allows clients to inject more transform ops into the same dialect, as long as they respect some of the preconditions of the dialect. The mechanism itself was mostly available in MLIR, but we had to modify it a bit so we can actually have the ops in the same namespace and so on. We also have ops that perform transformations themselves, things like, I don't know, loop fusion or tiling, or things like combining a couple of primitive ops into a higher level op. But we also have transformer ops. So we can have ops that control the application of transforms. So we can do a transform, then do another transform, then do another transform. We can have a for each, we can have a try, catch, try something else block. So we can basically expose parts of the logic of how the transforms are applied or decided into the dialect, and that can also be part of the schedule generation scheme. And most importantly, well, it's a dialect, so it's round trippable. We can have textual IR. This lets us separate the compiler that only needs to know how to implement a specific transformation from something that generates what the transformation are, which here I call schedule generator and schedule applicator. Both can be compiler, but we can also separate and have compiler as a more simple schedule applicator and have an external tool that would produce more complex schedules. Specifically, I'm thinking about a machine learning model that would look at the input program and say, well, a good schedule for this program would be this one based on a learned heuristic. It can also be human. It can be somebody who just types text. It can be a scheduling language. So we can, if we want it, we can build a DSL that produces this, build a compiler for that DSL without changing the compiler that compiles the actual payload. So if you look into more of the details, we can do it by example. So the very basic case of the transform dialect starts with basically two modules. They can be nested, they can be adjacent, same file, different files, doesn't really matter. The point is there are two modules. One we refer to as payload IR, that is the IR we transform, and another we refer to as transform IR, evidently that's the IR that guides the transformation. In the transform IR, when we start, there is a top-level operation. Here it's a sequence. It's very simple. As the name says, it just applies things in a sequence. And it takes a bunch of parameters. Here there's only one, and it's called a root. It's basically the top-level payload IR that we want to modify. If you are familiar with path management, that would be the root operation of your path. So we are not supposed to look at or modify the operations that are outside the scope for parallelism, basically sanity reasons. A big thing we can have in the transform dialect is typing. So we refer to operations or values in the payload IR by introducing SSA values in the transform IR. So here we have a handle value, which can be thought of as a pointer to operation, or to be more precise, a list of pointers to operations, because this thing may contain multiple operations that are associated with them. This handle value corresponds to an object in payload IR, and we can manipulate it. The value is typed, and the type describes some constraints on the operation it is associated with. So here it's the type as any op, but it can also be a concrete op, an interface, or basically anything we put in the runtime verifier of this type. Why it's good? It lets transformations to make explicit the assumptions they make about operations they transform. So if we have a loop transformation, it makes an assumption that the operation star it works on is a loop. Typically, it means implementing a loop-like interface, but it can also be something more complex, and the transform dialect infrastructure will take care of verifying whether the operations associated with this handle value satisfy the conditions or not. And if they don't, it will just return failure and provide you with an error message. One of the most important things why we started designing this is the possibility to change transformations. So we quickly realized in high-performance code generation that we want to keep transforming the same part of the IR without necessarily going over and over again the entire module. So here on the slide, we first want to match all the operations that are tileable. There's usually a handful. This might be perfect loop tests, this might be linear operations, it might be tensor operations, basically anything that has a tiling interface. And we say, well, those operations, we want to tile them. We don't care about anything else. And this is done with the tile to SCF4, which is one of the things we have. That tiles the op, so it tiles all of the operations that are associated with the handle and produces new things. And here you can see other types, that produces a tiled op and the loops that were produced. And because we are tiling to SCF4, you can see that the type of the result is transform op of a specific kind, SCF4. Now we can take the result of the tiling and tile it the second time. We don't need to go over the IR again. We don't need to go and check what is tileable. We just can keep transforming the same operations we matched before. So now, for example, we tile twice, and we want to vectorize the result. You might notice that I'm tiling with size 4, which happens to be the vector size on my machine. So now I can say, well, the loop that was produced by the second operation of tiling needs to be vectorized. And that vectorization is really simple because, well, we have just guaranteed that the loop we produced has exactly 4 iterations, or at most 4 iterations, depending on how you implement tiling. We don't need any magic recognizing that this is a loop, this is a loop with 4, this is a vectorizable loop. We know by matching that it is vectorizable, we know it has 4 elements, so it becomes an easier rewrite. And what's more interesting is that all the other code will not be affected by this transformation. So we can still decide to vectorize it differently. And then again, I will touch on this later on. But an important part, in addition to chaining, we can target transformations very precisely to pieces of the transformation of the translation unit that we want to optimize in a more advanced way than we would normally do with like a generic pass. We can also do choices that would be suboptimal in the general case. So we can decide to vectorize for tile something that we know will benefit from these transformations, even if the transformation may not make sense in the general case. I have one more example where we can reuse with unrolling, but it just reuses the same part. Another kind of values that we can use in the transform dialect is called a parameter. And unlike a handle, a parameter does not refer to an object in the payload IR. Instead, it's a value. So it's a value that is known at transform dialect execution time, which is likely compile time, but not necessarily. And why we need values? Well, we don't always want to tile everything by 32, or we don't always want to hard code things like tile sizes or the amount of fusion or basically any numeric quantity. What we may want to is we may want something or somebody to provide this value, either based on what we matched before or based on some criteria related to the target machine. So this can be modeled by having these parameters, which are basically values, or list of values. There is a bunch. So here I'm using parameters that just points to a 64-bit integer that can itself be used as style sizes. Some of the operations already support these, some do not yet. It is a relatively recent addition, but that gives you a way to connect to a heuristic or to something that produces numeric parameters for something that would be otherwise a fixed schedule. Okay, that's how it would look like in the IR if we were just to read the IR. And all this needs to come as implementation. Well, since these are ops, you start by defining these as ops in a dialect, just the usual stuff. And what you need to do additionally is to implement the transform op interface. And the interface is really, really simple. There's just one function, it's called apply. This function is called by the transform dialect engine or interpreter when it decides to execute a transform op. It has two things. It has a result structure it has to populate, and it has a state it can query when performing the transformation. These two values basically let an individual application interact with the entire transform dialect infrastructure. And what they really mean is how do you establish or analyze the mapping between the values we have in the transform IR and the parameters or the objects in the payload IR. So it's basically a bidirectional mapping between SSA values in one piece of an IR and objects in another piece of IR. That's pretty much it. The internals of this op can be arbitrarily complex, but there are some additional things we can do to make it easier for tools and also people to reason about this. For example, we can mark side effects of an operation if it somehow rewrites or removes certain kinds of operation. So we can say it writes to the value it takes when it rewrites it, or it frees it if it erases an operation. So this value should no longer be used. Again, as a reminder, a handle value is basically a pointer to an operation. So it is subject to anything you can think about a pointer is. So as a pointer, it can alias, so we may have multiple values pointing to the same operation. It can be freed, so you can have use after free, and so on. And we also have a lot of infrastructure in place to actually catch those as interpretation time. One of the things that are worth noticing here is this diagnosed silenceable failure that we needed to introduce in addition to the usual logical result, because we wanted transformation to be failable without necessarily failing the entire application of transformations. What I mean is, if you have an operation that just wants to match something in the payload IR and it fails to find it, well, you probably want to know that it did not match anything, but you also wouldn't want to stop the entire path that runs this because something failed to match. Similarly, some of the transformations may decide that failing to perform the transformation is not critical for progress. For example, we may say, well, let me unroll the loop if it's sufficiently small, and if it's not sufficiently small, just keep the loop. So that transformation should not fail, but we may want to know that it tried and didn't do something. So this silenceable failure is basically a three-state result. One is success, one is definite failure, stop everything now, and one is what we call a silenceable failure, which is a combination of a failure state and an error message that we can report to the user as a real diagnostic or as a debug output. Whoever calls this transformation may decide to either propagate the failure to their caller or to suppress it and say, well, that was fine. We looked at what the results and the state are. They're basically the connection to the mapping between SSA values in the transform dialect and objects in the payload layer or parameters. And that's pretty much it. So we can look at a couple of transforms we have upstream, but So far, I know of at least 4 different projects that started using transform dialects, and most of them are not upstream. So I'll take this as an opportunity to encourage people to put stuff upstream. Most of the things we did are connected to the lineage dialect and more generally to the idea of structured operations. So most of the transforms are prefixed with the structured thing. So transform.structured.something operates on structured, mostly not ops, but there are some other ops that it can operate on. And this double prefixing actually lets you understand that this transformation comes from the structured dialect extension of the transform dialect. And if it was a loop extension, it would be transform loop. If it's a lineage, it would be transform lineage, and so on. So we have the transform structured tile. Well, I like tiling. And as you might expect, it takes an open iteration space and a decomposed iteration space into smaller iteration spaces with the same open side and loops outside. It takes sizes as either parameters or values computed by some other ops and produces handles to loops and the tiled operation. You can check it. There is a sequence, and sequence is a built-in transform operation. So it's in the transform dialect, not in an extension. It doesn't have a second prefix. And what it does, it combines other transformations. So it's one of the top-level things that we can use, along with for each and several others, that says, well, when you execute this, the only thing you need to do is go over all the nested transform operations and apply them in order. Transform alternatives is another example of a top-level operation where it will go and try each of the blocks it has. So it will go and try the first block, and if something fails, but fails not definitively, so produces a silenceable failure, it says, well, it's okay, and goes to the next block. If that fails, it says, well, that's also okay, and goes to the next block, until either there is a block that fully succeeded, or it reached the last block, none of the blocks succeeded, at which point it will return a silenceable failure to its parent. So it will return a failure that can be propagated further on. We can have nested sequences, we can have for each, or other things. Or if we reach the end result, the top-level operation, it will end up being reported to the user as a diagnostic. One thing that we would like to have and haven't had time to implement yet is some sort of macros, not necessarily functions, but named entities that we could call onto or include. So here I put to be done transform dispatch, something that would take a symbol as a name and say, well, now go execute transformation described in that symbol and come back to me. We do not necessarily want full-fledged control flow and a call stack, at least not right now. So think more of a macros. And macros would be really easy to add, and we can use the infrastructure that is already in place in MLIR to basically do an inline pass, so the interpreter doesn't even need to know about these macros. And I think my final example of a transform we can have is a merge handle transform, which is a utility thing that does not affect the payload IR in any way. It basically takes multiple handles, so lists of pointers to operations, and it produces one single list from those. This might be useful if you want to first transform pieces of payload IR separately, and then you want to transform them in the same way. This can be done by calling to a macro if you had them, but this can also be done by saying, well, now all these things that I had before as separate pointers or separate lists now become a single list that I will transform homogeneously. We already mentioned that a handle value is essentially a pointer, so we may have a dead-end pointer problem. And it's more or less a data flow problem. So it's really a use after free that is possible with these things in presence of aliasing and in presence of handles pointing to operations contained in other operations. So imagine a situation when you have a function and you have a handle to operations inside the function. When you erase the function itself, all those handles become dead. This needs to be captured, and we do so by running a sort of ASAN equivalent. So we can keep track of handles that are being consumed through side effects, so something has a free effect. And we will know that any handle pointing to the same operation by aliasing, or any handle pointing inside that operation in the payload, becomes invalid. So next time that handle is being used, the infrastructure will be able to complain. Obviously, that requires some runtime checks that we do, and that comes at a cost. We can also do a smaller version of this by running a data flow analysis. And by saying, well, if we know that we have a free side effect on the handle, and then we read it, that would not be valid. So basically, leveraging the data flow infrastructure that we already have in place. So you see, it's really nice to have this as a dialect. We are able to statically and relatively inexpensively check for use after free and similar problems with the transform dialect. Well, that's kind of the point I was trying to make. Since transforms are just IR, we can analyze and we can also transform them. So we can do inlining, we can run analysis on them, we can do common sub-expression elimination, and so on. Basically, anything that would work on any generic IR would also work on a transform IR. So we can think of dumping a lot of possible transformation strategies and trying to find a single combined strategy that works for all the cases we care about. Okay, that basically explained the general concepts of what the transform IR is and how it can be used. And now comes the question, so what? Having this, well, we had a specific problem to solve with chaining, but it is also an important step to understanding how do we want to design a compiler when we try to generate good performance. And here comes what I call deep and wide transformations, and what I tried to refer to previously. So if you look at how a compiler is usually done, including many MLIR-based compilers, a compiler runs multiple passes, and each pass applies to the entire translation unit. So typically a module, well, we have function passes or operation passes, but in the end, they apply to almost everything. Many of the passes try to filter out the cases where they apply and basically bail out early. But what happens here is we have a program transformation that applies to the entire program. That's what I call a wide transformation. So if you have a tiling pass, it will go through the entire module or per function in a module and try tiling all the loops. If you have vectorization, it will go through the entire module and try to vectorize everything. And it's not necessarily what we want. What we want, especially when we want to generate really high performance code, is to precisely target a very small portion of IR that we want to optimize, and we want to spend a lot of cycles optimizing. And for the rest, we just do best effort or do just lowering. So we can think of this as a sort of Pareto principle in compilers, where we want to spend 80% of the time optimizing 20% of the program. And we don't want to spend that amount of time and effort optimizing the rest, because like costs and similar operations might not even matter. So here comes what I call deep transformations. And transform dialect was mostly intended to do this kind of deep transformations. So for example, if we want to do double tiling and vectorization for matrix multiplications, and we want to decompose a convolution to matrix multiplications again through im2call and optimize it similarly. We don't care if there's an element-wise. That's an easy thing that doesn't affect the overall performance. Or we may say, well, we're running this program and we've done profiling and we know this part is really the part that takes most of the runtime. So that's the part we want to optimize. And we don't want to spend time on anything else. And now what happens is we actually need to combine these two. We have two pieces of the infrastructure, one that supports deep transformations, one that supports wide. We currently run transform dialect as a pass, so it runs within a pass. We may discuss on how this can align more with the pass infrastructure, or should we lift it even above being an individual pass. But the overall scheme will look something like this. So first, we will run a set of targeted deep transformation on pieces of IR. For example, here we will go and tile as a means to introduce loops. And then we will go and introduce loops in all the places that don't have loops yet. So we'll do a deep pass or a deep transformation, then a byte transformation. And then after that, well, let's assume we are targeting a GPU. So for matrix multiplication, we want to put one of the inputs into a shared memory based on how transposed they are, another into registers. So we can do that as a transformation. And we only care about doing that for matmul. Moreover, we don't necessarily want to do it for anything else, so we don't exhaust the shared memory resource we have. So we really want this to be targeted. For convolutions, you might want to do something else. And for other cases, you might want to do something else entirely. But the point is, we want to transform a piece of the input IR very precisely. And then we want to say, well, everything else should go to some buffer. And we want to optimize. We want a globally optimal decision, provided the decisions we already took locally. Because those are the ones that likely matter. And the rest, well, they do matter, but not as much. And so on. We can, for example, map to tensor core. But again, the important part is this alternation between deep and wide passes. And now that's a good question. That's how it is currently structured. So on the right, that's how it currently works. So we have a pass that does multiple applications of the transform dialect to different pieces of the input IR. Then another pass that does kind of cleanup work. Then another pass that does transform dialect, and another pass that does, or multiple passes that do this cleanup and best effort work, and so on. We can also say this all happens in one big pass. We can also say, well, this white thing can also be controlled by the transform dialect. So for example, we could have a bufferized transform that does a pass. We can run a pass manager from within a transform ops apply method. I think what's important here is this everywhere or everything notion. So introduce loops everywhere or bufferize everything. And what this gives us is a notion that doesn't really exist yet, but I think it's there, and it would be really helpful if we could somehow materialize it in the infrastructure, in the notion of what I call is a state of the IR. And by state, I mean there are some conditions that the IR satisfies that are not necessarily the validity condition. So it's not like something we can put in a verifier, but it is a precondition for the next stage of transformations to happen. So we can, like, mostly these are associated with a type system change. So if you talk about an ML compiler, it starts in the tensor world, and at some point we want to map all tensors to memory. So tensors go to member of our pointers. And further transformations and passes expect that the IR no longer has tensors. It's not that that IR is invalid or having an IR with mixed tensors or end membranes is invalid. It's just that further transformations expect that. And this expectation is at best written in English in a pass description. At worst, it's not stated anywhere. And we have several of these, and they're typically boundaries of lowering stages. So we start with a graph IR, and we can either go to buffers or introduce loops. So one of the stage changes would be, well, now we have introduced loops, we can do loop transformations, or now we introduce buffers, we can do memory optimization. And then there are several others, like doing transformations that go to LLVM dialect or to SPIR-V, or basically anything that either prepares the input from the front end to whatever the mid end can optimize, or whatever came out of the optimizer that needs to go to the backend. It has some preconditions, and we don't really have a good way to encode those. And then now, if we had that, and if we could connect them to these wide passes, that would let us structure the compiler in a better way and better combine these deep and wide transformations. So what I noted here is another idea is we could kind of look at this and have transforms as in functions that actually do transforms describe the effects they have on the state of the IR. So we can have a pass or a transform or anything that says, well, what I am guaranteeing is that as a result, I will not produce tensors, or I will convert all tensors that I know of to memrefs, and so on. Based on this, we would be able to automatically construct a pass pipeline or a transformation pipeline that achieves the desired state. So we can go and say, well, compiler, please vectorize everything, and it will go look at the effects of individual transformations and try to combine them such that on the input IR, we will have enough transformations to actually achieve the vectorized state. This comes with problems. So combining these things, and especially being able to keep transforming these precisely selected pieces, is difficult. So we need this white pass to somehow preserve the handle or preserve the notion that this operation before the pass is that operation after the pass. And that is not readily available. So we have some capability within the transform dialect to actually maintain that across a path that is based on a pattern rewriter. But in general, combining these deep transformations and precise targeting with wide passes that go over everything requires either that or rematching. So we can run a wide pass and say, well, we know the effect that this pass will have on the IR. So we can try matching again the computation that we matched before. So if we had a matmul and we ran a pass that introduces loops, well, we know matmul has 3 loops. So we can go and try matching those 3 loops. Not ATL, but having the dialect as a declarative thing, and provided we have this effect system, we would be able to rewrite that matcher based on the fact of saying, well, after those effects, the new matcher will look like this. Another thing that we hit repeatedly is canonicalization. And I don't think this is actually specific to transform dialect or any of the transformations we make. But what we've seen is oftentimes we want some sort of canonical form to be produced. And what the canonical form is changes quite frequently. So people keep adding and sometimes removing canonicalizations from ops. So we don't really want each of the transformations we have to know what is the canonical form today. At the same time, we don't necessarily want to run the canonicalizer pass as a pass after every small transformation. One, because it's just expensive, because it will go through the entire IR, modify a lot of places, apply a lot of patterns, and 2, it might break the tracking. Because the canonicalizer pass is one of the wide transformations, well, it may just erase the operation you were targeting in the first place, and you have no idea that it happened. Again, we have a workaround, so we know when the canonicalizer will remove that, but it would be nice to have some sort of local canonicalization that we could apply after rewriting a part of the IR and only apply it to that part of the IR and only apply it to operations we care about. We can also think of canonicalization with respect to these stages or states of IR, because one could argue that canonical forms might be different in different stages of compilation. So in some cases, we might want to, I don't know, preserve loops even if they're trivial. In some other cases, we might want to eliminate trivial loops, and so on. So this brings me to several points I want to make about compiler design and what I think we should focus on in the future when working on the MLIR infrastructure. One of that is looking at the rewrites. And a lot of our passes in MLIR are using rewrite patterns. And one of the things that really helps with composability chaining and reasoning about rewrites is rewrites having results and not just status. So if my loop tiling pattern, which we do have, produced loops and not just true or false as a result of tiling, well, then I can actually chain a transformation on those loops. It doesn't require transfer dialect. It doesn't require any dialect, just requires C++. But today, if you wanted to chain that without having to go and rematch everything and apply more patterns, well, we would need to attach an attribute and then here another pattern, look for an attribute, and run the risk of a third pattern removing that attribute. So a simple thing as returning what the main result of a rewrite is could make the composability of rewrite rules much better and much faster. We need some infrastructure for these write transformations to notify us or notify the compiler about some of the actions they're doing. So you might have seen Maddie's proposal on operation listeners, something like that, but at a higher level. So knowing that an operation is being erased or being replaced, and replaced with what? Knowing that operation is being fused is really important to understand how the IR is being changed if you want to keep changing some of the pieces that we have handles to. Local canonicalization I mentioned on the previous slide, it's really nice to have this sort of cleanup capability and say, well, I have my transactional transformation here, and after it's done, something will come and clean up after me. So I can emit code that is not necessarily canonical or optimal, but I also don't need to pay the full cost of running the canonicalizer. And more often, observation when we need to design a dialect that is specific to transformation. What we probably want is to design interfaces, and we don't necessarily care about ops. So the transform dialect itself has like 6 ops. And everything else that the infrastructure does is done through interfaces. And that so far has been a very good experience, and we can plug many more things that the dialect has no idea about. So we can run it downstream, out of the tree, and it still works with minimal changes. One other thing I could touch on, and that I briefly mentioned in the beginning, is that having transforms expressed as sort of IR allows us to externalize compiler heuristics. What I see currently as a way to apply it does not need to be the only way or the main way we will implement, is some sort of separate database or I don't know, a library of transform recipes that contain both the recipe itself, so what the transformation is, and the criteria that the IR we are transforming needs to satisfy for the recipe to be applicable. These criteria can be simple, like I just need a DAG of ops that I know how to transform, something like a DAG that represents an attention in ML. They can also involve things like parts of machine modeling, they can involve size and so on. So they don't necessarily need to be simple. They can also be parametrics. They can look into details of what we're optimizing. They can look into something that describes the target machine that we don't really have an MLIR yet. And what's good about this, these can be produced separately. So I can go and write them, or somebody else can go and write them. Or we can have a tool that we teach to write them. Can be as stupid as let's just try generating all valid permutations of ops, and we know what the ops are, and as smart as designing a reinforcement learning algorithm that produces a schedule based on what it sees as input layer. So I have an example that I will probably just skip over and share the slides. The interesting part here is that we can also separate the recipe where we say what we transform from the strategy that decides on specific details such as sizes, amounts, based on parts of the input. So to summarize, if you joined later or didn't hear everything, we have a thing called the transform dialect, which allows us to express schedules in MLIR. And schedules is a part of IR that describes how the compiler should transform another part of the IR. It's a dialect, it's an MLIR, so it's extensible. It's even more extensible than most of the dialects we have, because you can inject custom operations and custom types directly in the dialect and have it work with it seamlessly. We would like to see better infrastructural support for these transformations. So we are trying to build it with this dialect thing, but we also need support from canonicalization, from rewriters, listeners, and so on. And we hope that having this will create opportunity for interesting research work on the edge of compiler and ML. So far, we've been doing a lot of work on compilers for ML. Maybe it's time for somebody to do ML for our compiler. I think that's all I have. So thank you. And if there are any questions, please go ahead. No questions. So I assume it's all good.
Maybe.
Okay.
So on one of your previous slides where you talked about the alternative case, we could say transform to alternative. What's in the event that they all fail in a suppressible way, what does it actually return? Is it one of the failures, or has it got its own failure?
So actually it will return a failure that contains all failures.
Okay. Yeah, that makes sense. Thanks.
So most of this is available upstream, so you should be able to just go compile MLIR and try their tests. Basically, look for test transform dialect interpreter and look at tests that use that. Any more questions?
Yeah, Alex, I have a question regarding the deep optimization on matmul and convolution, where I see the vectorization pass now happens above the loops everywhere. And as we know, most of the vectorization pass happens after by seeing loops and vectorizing loops. So now do you foresee that before you have loops everywhere, you already have vector types because you are vectorizing quite early onward?
So we have a capability to vectorize early. So we have a vectorization that looks at linear generic on tensors and transforms that to linear generic on tensors of vectors or vectors directly. And the point is that this can happen in the cases we care about. So we can go and vectorize a matmul and make sure it maps to the right vector dialect level operations. And at the same time, we can keep the rest unvectorized. And at some point, we will call the loop vectorizer after we introduce loops, but it will not touch and not undo any of the decisions we made previously. So it is composable with a loop vectorizer if you want to, but it's also at a higher level if you want to. Okay, it's more about flexibility.
Got it. Thank you.
Alex, I had a question.
Yeah.
In one of your slides, you mentioned we should change the rewrite patterns and transformations to return results. But I'm guessing it's not going to always be enough to not be able to get some handles invalidated. And I wonder if you have a grander plan or like an idea of how we can better handle cases where we lose handles because of those kind of transformations.
Yeah, so there is, I think the specific situation where this might happen is when you erase or somehow recreate the ops that are not considered the main result of the rewrite.
Right.
And that, well, if the pattern is written carefully, it should be used in the rewriter. And then the rewriter will get notified if an op has been erased or validated. So we can latch onto that. The stupid thing, we can just either invalidate the handle or erase the association with this payload op and saying, well, if it was associated with a list of things, now it's a list of one thing less. Ideally, we would have a sort of interface that we would attach to ops that says, well, if an op is being replaced with something else, what is a meaningful replacement? So if you're replacing a lineal generic with the result of, I don't know, extract slice, well, the meaningful replacement is probably the other lineal op that produces the value from each extracting slice. But this sounds specific to either a transformation or an extension. So like if we're in a structured world, it's probably you want to find the other structured op because we are targeting those. So I would go for some sort of interface where an op or given a pair of like payload op type and transform op type that would say what is a meaningful replacement when the op is being erased. I don't know if that makes sense or not.
No, it makes sense. Yeah, that's a good idea. Yeah, I'm guessing it's a big challenge in MLIR. And
yeah, I think it's generally a big problem when we want to keep track of stuff. So at some point, okay, we should just pre-match. But for stuff like generics, well, there is like the way I see it, there is a monadic computation somewhere, and we just need to understand what it is. So for lineage, yeah, we always want to get back the lineage op because that's the thing we know how to transform. For loops, we almost always want to get back the loop. In between, I don't really know, and I'm not sure there is a nice closed set of transforms that we can design.
Yeah, makes sense.
Alex?
Yeah.
I have a question about the alternative op. What if we wanted not trying alternatives one by one until one succeeds, but trying multiple alternatives and choosing by some kind of a cost function? And maybe do this.
You
yeah?
totally can have an op like that. Please add it. So in practice, it's really simple. So right now, what alternative does, it takes a scope in which all transformations should be localized, and then it will clone it, assuming that a transformation can do some irreversible changes. So now, if you want to evaluate the result, you can clone it multiple times, transform each clone differently, run the evaluation function, and based on that, keep only one of the clones. So it should be really easy to add if you're interested.
Yeah, maybe even do this recursively. We'll try not to explode the search space, but have it kind of try multiple alternatives at multiple levels, right?
Yeah,
that would make
absolutely.
sense.
So you can nest alternatives as much as you want. There is always a question of how much stuff you clone because that's expensive. But then at some point we could look at predictions. So we could try like if the internals of each alternative have a declarative specification of the effects they do, we can try to use that to sort of lift the evaluation to before the transformation apply or before some transformation apply and sort of minimize this alternative choice.
Some kind of early pruning or?
Yes, some kind of that. There are a lot of things I can envision doing, but we don't necessarily have resources to do them right now.
Okay, thanks.
Which again, MLIR open source, please contribute. Put me as reviewer. I'll happily review patches to the transfer dialect.
A good question. Have you thought of use cases where these transformations happen at runtime? And if they need to happen at runtime, do we have the infrastructure necessarily in place for doing that? As an example, something like a parameter for the transform dialect can be only obtained at runtime. Some use cases like that.
Yes, so there are several scenarios. I mostly looked at a sort of runtime decision tree scenario. So we do not know the parameter at compile time, but we know the likely values for it. So what we could do is we could substitute the parameter with a constant multiple times repeatedly, run the transformation, obtain the IR, and then build a dispatch that will choose one of the precompiled version at runtime. So for that, we mostly have everything in place. I think the only thing that is missing is the description of how to translate the transform IR code into something like LLVM-IR. The rest will mostly work out of the box. So if you really need to JIT compile, so like the other extreme, well, you need you would need to extract the transformation and the dialect into a separate JIT thing, like a separate binary that only has a transform dialect and the related transformations.
Right.
And then do it like MLIR CPU runner does or used to do. It would consume IR, inspect it at runtime, and then run the transformation, generate LLVM-IR with passes, JIT compile that. But with the current setup, I expect that to be incredibly expensive.
Got it. Thanks.
I mean, it's also something that we should explore, but my primary use case was that like more multi-versioning than JIT.
Got it.
Any more questions? We're also running out of time. So I suppose if there are more questions, feel free to reach out to me on the forum or Discord. Thanks, everyone, and see you at the next ODM.